Hello, in this video we're going to look at a full curve sketching process. So I've got the process listed here in terms of points. It doesn't necessarily mean that this is the order you proceed, but it is a pretty good order. So identifying domain restrictions, determining straightforward x and y intercepts. So y-intercepts should always be pretty straightforward. X-intercepts don't spend a ton of time if it's going to take a lot of algebra. Is the function even or odd, or maybe neither? So that's what happens if I replace x with negative x. Does it give me the same function, or does it just do a vertical reflection of the function? What do you already know about its basic behavior and shape? So if it's polynomial and so on, is it increasing, decreasing? Use limits to formally determine any asymptotes or points of discontinuity. Use the first derivative to determine intervals of increase, decrease, find any minimum or maximum points. Second derivative for concavity and points of inflection. Sketch the function is the one that you probably should be doing kind of all along. Sketching your asymptotes on there as you determine them, putting x and y intercepts on the graph and minimum points and so on as you determine them, so that at the end you can get a pretty good idea of the sketch. So let's look at how this plays out in the function y equals x squared over x minus 2. So first off, I have the fairly obvious domain restriction that x cannot equal 2. So that tells me what limits I'm going to explore for a vertical asymptote. I can also see here that if I substitute x equals 0, y would then be 0. So I have a function that goes through the origin 0, 0. If I consider what happens if I replace x with negative x, so to determine parity, is this positive, is this even or odd? What I see is that this is x squared over negative x minus 2. It's not the original function, and it's not the opposite of the original function either, because that minus 2 is still negative. So this is not even or odd. So there's no symmetry there. If there is symmetry, that's helpful, because it means that for every, so for example, if it's even, if I find that there's a minimum at 3, then I know there's a minimum at negative 3 as well. And it saves me having to calculate the y value twice, because if when x equals 3, y equals 7, then when x equals negative 3, then y equals 7 again. But in this case, I can't do that shortcut. So for the vertical asymptote, if I consider the limit as x approaches 2, and I'm going to consider it from both the right and the left, because I can see right away that there's no common factor of x minus 2. So this isn't going to be a point of discontinuity. I'm not going to have a finite limit. So the limit as x approaches 2 from the left of x squared over x minus 2 is going to be approaching, so 2 squared is 4 over a 0 value that is going to be slightly negative, which means from this side it's approaching negative infinity. And as I approach 2 from the right of x squared over x minus 2, this is going to be approaching 4 over a slightly positive 0, which means it's going to be approaching positive infinity. I like to, as I do my work on the left-hand side of the page, on the right-hand side, I will then give a summary of the key points that I want to put onto my graph. So I know that I have the point 0, 0. I know that I have a vertical asymptote at x equals 2. And specifically, I'm going to make a little sketch so that when I go to draw my graph, I'm seeing it go towards negative infinity on the left and positive infinity on the right. What this means, actually, this already tells me something that I will now expect to see in my first derivative test. I will expect to see that both to the left of 2 and to the right of 2, this function is decreasing. I also am kind of expecting downward concavity on the left and upward concavity on the right, although I can occasionally see something different from that. But having that sort of sense of, okay, this is what I will anticipate seeing when I do my first derivative test can help with some error correction if I do make mistakes along the way. Now, as far as a horizontal or slant asymptote, the degree of the numerator is 1 higher than the degree of the denominator. So I am expecting a slant asymptote. So I'm actually going to do the division here and convert it into quotient and remainder form. So I have 1 as the coefficient of x squared, 0 is the linear coefficient, and 0 is the constant coefficient. So when I do my division, I get this, which means that y is equivalent to x plus 2 plus 4 over x minus 2, which means, once I do that, that when I take the limit as x approaches infinity of 4 over x minus 2, that is equal to 0. So what that tells me is that there is a slant asymptote at y equals x plus 2. Now at this point, if I had a piece of grid paper here sort of separately, mine I'd have to scroll down, so I'm going to just wait and put everything on the graph at the same time. But if I had a separate piece of grid paper to where I was doing this analysis, on that grid paper I would have put the point 0, 0, I'd have drawn my vertical asymptote, I would now be drawing my slant asymptote. But I would come back and do that momentarily. Okay, so let's move on now to the first derivative test. So when I'm taking the first derivative here, I've got the quotient rule that I have to use. So deriving the numerator gives me 2x, derivative of the denominator is 1. Sorry, that's obviously not what I needed to do, times x minus 2 minus the derivative of the denominator, which is 1, times x squared over x minus 2 all squared. I definitely want to simplify this for a couple of reasons. I am going to have to take a second derivative, so I definitely want to simplify it, but also I need to find critical values. So we have, this is 2x squared minus 4x minus x squared over x minus 2 all squared, which means that I have x squared minus 4x over x minus 2 all squared. This is the form I'm going to use for my second derivative, but I'm going to go one step further and factor for critical values here. So my critical values for my first derivative test are the zeros. So the critical values are when x equals 0 or 4, but also where x does not equal 2. Now I already knew that that was a non-permissible value from my original function, so it definitely has to be a non-permissible value in the derivative. It's critical in that it is an asymptote, so I already know what the graph looks like around there, but it divides out intervals for increase and decrease because I can have different things happening on the left side of the asymptote than on the right. So when I'm doing my first derivative test and checking my sign table, I need that divider. So I've got 0, I've got 2, I've got 4. I usually make a distinction so that I am aware that that is an asymptote, so it's not going to be a minimum or maximum no matter what happens. So then I have factor by factor what's going on. So x minus 4, the x minus 2 squared I don't really have to include because it's always going to be positive, but I'm going to include it anyway. So x is negative in the interval less than 0 and positive elsewhere. X minus 4 is negative in all the intervals less than 4 and positive greater than 4. X minus 2 squared is positive everywhere. So overall, my first derivative is going to be positive for values less than 0, negative for between 0 and 2, negative between 2 and 4, and positive greater than 4. Notice that around 2, that matches what I was expecting based on what I knew about behavior around that asymptote. I was expecting it to be decreasing on both sides. But what this now tells me is that I have a max at x equals 0, and I have a min at x equals 4. So what I'm going to sort of summarize on the left-hand or right-hand side of my page is I have a max when x equals 0, and that was the point 0, 0. And I have a min when x equals 4. So I now have to calculate what is the value of y when x equals 4. So that was x squared over 4 minus 2, so 16 over 2. So that is the 0.48. So I now know I have a minimum at the 0.48. This is starting to come together now. I just need to do one last check for concavity. And so on to the second derivative. And like I said, I'm going to use this form of the first derivative to take my second derivative. So d squared y over dx squared equals derivative of the numerator is 2x minus 4 times the denominator minus the derivative of the denominator. I am going to multiply by 1 here. I'm writing the 1 just so that we don't forget the chain rule when the coefficient of x is something other than 1. And then times the x squared minus 4x of the numerator. And then all of this is over x minus 2 to the power of 4. So simplifying this so I can find critical values, I am going to think about this is 2 times x minus 2, because that is potentially helpful. So that is helpful in that I now see I have a common factor to both parts of this numerator of 2 and then x minus 2. What is left of the first term is x minus 2 squared, which I'm going to distribute out, x squared minus 4x plus 4. What is left of the second term is the x squared minus 4x, but that was minus, so it becomes minus x squared plus 4x, which is all over x minus 2 to the power 4. So the stuff inside the square brackets simplifies pretty nicely just to 4. So I've got 4 times 2 in the numerator, which is 8, and over x minus 2 cubed. So this derivative has no zeros, and the only critical value is the non-permissible value. So x cannot equal 2. I am expecting, based on the fact that I know there's a maximum at 0, so to the left of 2, I'm expecting this to be concave down, and to the right of 2, I'm expecting it to be concave up, because I know I have a minimum. But I'm going to confirm that just to make sure, because it's, we've got lots of places to confirm here and make sure that we are seeing what we expect to see and just making sure that we know what this graph is going to look like. But again, that's an asymptote, so I'm keeping clear. There aren't going to be any inflection points here because I can't be at an inflection point at a non-permissible value. The numerator is always positive, so I'm not going to bother including it because it doesn't affect the sign. X minus 2 cubed is going to be negative if x is less than 2 and positive if it's greater, which means I have exactly what I expected to see. Downward concavity, upward concavity, no inflections. So with that, we can start actually putting together the graph. So let me get my grid in here, make that a little bit bigger. All right, so I'm going to get my asymptotes on here. I know that there is a vertical asymptote at x equals 2. So I'm going to put that on here and I am going to label it. I know there is a slant asymptote at y equals x plus 2. So I'm going to draw that on here as well. So y equals x plus 2, making sure I get the slope right. That is a slant asymptote. So just quickly getting this line on here. I know I have a point at 0, 0. And I know I have a point at 4, 8. So 4, 8 goes here. Based on the fact that this function has to be approaching those asymptotes, that it is increasing up to 0, so something like that. That is a function that is increasing and still approaching that asymptote. It's decreasing after 0. So this right here I'm going to label as a max. And it was decreasing between 2 and 4, and then increasing after 4, and approaching those asymptotes, and this is a minimum point. So there's my sketch, which with all of the key characteristics labeled.